Here we are live. Let's see. All right, computer says yes. All right, so ladies and gentlemen, boys and girls, hackers and noobs, this is pwn.college for CSE598. We are currently discussing primitives in memory mastery. For those that have not seen this website, pwn.college, is free and open to everyone. Just go to pwn.college. You can create an account, and as it says here, you can learn how to hack. This is set up in kind of a martial arts style dojo. Once you've created an account, you can hit dojos. This will show a progression of content with a basic expectation of computer science, like an undergraduate understanding. We take you from learning kind of the terminal and assembly all the way up to doing like microarchitecture exploitations and some more complicated things. And so you can progress along here with this belt. Now, this material is also used for a course at ASU University, actually a number of courses as you see here. This particular stream is about CSE598, which is some of the advanced material. Currently, as I said, we're talking about exploitation primitives. If I click right here, what you'll see is there are a number of pre-recorded lectures, we have some slides, and then down here we have challenges. This is where things get spicy. If we click on level 1, we can hit start or practice. This will start a challenge. We'll see a little prompt here that says, challenge started in just a moment. Right now we are at near peak usage for those here in class. I've already noticed a fantastic delay from users. We're like T-3 days right now, right?
Oh God,
so
it's gonna be rough.
Right, that's another reason why like we'll see how this weekend goes. So if I click on workspace, I get a 502 bad gateway error. If I refresh, I now get a VS Code interface. This is in our web browser here, and so this allows us, see if I can remember how to use VS Code. I will never remember what keys are needed for a terminal in VS Code. And this gives me a live terminal and an editor up here that you're probably familiar with, where I can then work with these challenges directly in a website. If that is not your speed or you want a graphical tool, we do have a live VNC interface here via this desktop link. From there, for instance, one thing I may want to open that may or may not work is IDA. And so this challenge here, I'm going to open in IDA, which is what we're going to be taking a look at today. All right, it's not down yet. If I hit tab, I get my decomp right here. Now, me personally, I like working in the terminal. So what we can do is, once configured, which these steps are on the home page, you can SSH directly to that same interface with SSH hacker at dojo.pwn.college. And now I have a terminal session that is in that same challenge instance. So you can use these challenges to verify your understanding and learn along with us. So today we are looking at primitives in memory mastery. When I looked earlier today, this is office hours, so it's Q&A, live demos, things will explode and not work.
Why is your rank column so large?
Why is what?
Your rank column in this table.
That's the one over here. That's just an alignment thing, like that. Where do you want it? You want it just everything equally distributed?
I don't know. Mine looks like this.
Oh, okay. No, that's a Safari thing. Okay. Yeah, there's another interesting Safari thing for people. Safari bug for the rank, where if somebody has collected a sufficient number of badges, their row is twice as thick. But it only occurs on Safari, and we haven't like delved into it because it's not that critical. So I mentioned when we first kind of launched this with the class that this module will be like one of two things. You'll have one of two experiences, right? It will either be I solve like level 1, level 2, I have written an exploit, I've written some well-structured Python functions, and I can reuse these and plug along, and you're just going to rip through in like a day up until like 9 or 10, because 9 and 10 are a little bit different. Or you're going to write an exploit, or fail to write an exploit because the initial hill there, difficulty curve, is quite steep because you have to create these primitives before you can reuse them on all of these challenges. And then alternatively, if you didn't write your primitives well, right, or consider all of the different ways you may want to use these primitives, you may find, hey, my arbitrary read doesn't work, or hey, my arbitrary write doesn't work on this next level, right? And that's just because you haven't considered some subproblem that exists in repeated use of these primitives. Now, I did kind of poll the people here ahead of time, and there are some people, which makes some sense looking at the scoreboard here, that are still stuck at the primitive writing stage. I do want to ask, did you see the pre-recorded lecture videos? Yes. Okay. Because what I'm going to do is going to be very similar to that, except instead of Jan doing it, it's going to be me doing it on the fly here. And so we'll see what comes out the other side, and hopefully whatever it is we're stuck on will emerge. What is today? Prim. We'll call it prime. Prime's a good word, right? 365?
Downstairs.
Yeah.
Downstairs, hang a right.
All right.
190.
Yeah.
Is the sign still out there, or did it fall down?
Yeah, it is.
All right, cool, sweet.
I just didn't see it.
No worries.
Okay. So we have this challenge here. And from class, we saw if we run it, it's going to accept network connections. And then we can connect to it. And we have commands like malloc, free, scanf, printf, send flag. Right? We've seen this kind of model before in the heap 1 module where we were messing around with tcache. Now, the important thing to pay attention to, since this challenge doesn't give us a whole lot of output, is how do we interface with this? A good way to determine that is to use IDA or some type of decompiler. We see here that main calls run thread calls challenge. Once we look into challenge, we can get some idea of how this works, what it is expecting. And now, in my opinion, the way to kind of start writing this, and this may be different than what you do, is I like to stub out little functions that do the interaction, right? So it wouldn't be wrong. Well, let me get my boilerplate here. User, what am I looking for? User bin and Python 3 from pwn import star context arc equals AMD 64. Okay. Then at some point I'm going to have p equals process challenge. What is this?
Maybe prime level 1.
Baby prime level 1.0. And then I'm going to have some type of remote connection, right? Because I'm going to connect to this. And we can do that with Pwn tools with the remote command. So I have localhost 1337. Right? This much I think we all have. Now, this is where the structure of your code, just in general, starts to matter. You could do something like r send line malloc 1, right? And we could just do that right here. And we could malloc 2. And then we could free 2, free 1, right? We could do something like this, and that would be perfectly fine. The problem that we can run into, though, is our code starts to become a mess, right? Because all of a sudden, it all depends on, well, is this thing right here, this magic value that's inside the string, is that correct, right? And so what I like to do, and it's not, it's hard to debug what exactly is going on, in my opinion. This is going to be an opinionated stream, unfortunately. So instead of having just send line, I would define some type of malloc command. It's going to take a remote and it's going to take an index. Now, I have some idea of what these later challenges are, and what I am writing right now, it will not answer every subproblem that exists in later challenges, just as an FYI. So you will want to iterate on kind of what is the methodology, what are the arguments of these functions and what do they do as time goes on. So I have this handy little malloc function. What is it going to do? Well, it's not really that complicated right now. It is just going to remote send line malloc index. You're going to be like, well, Robert, that's really lame, right? Like, what have you done? And I agree. And so I'm going to have the same thing here for free.
Probably want to make those format strings.
I probably do want to make those format strings. So now my code becomes malloc R1, malloc R2, free R1, free R2. Now, the reason that I like doing this and having kind of a function that wraps this is, well, what if I want to debug some of this, right? Well, it's pretty easy for me to say log info, what do I want? In malloc index, and that will also be an abstract. Right? And so now I have that in every action, versus if I were writing all of this in line, I have to add these print statements everywhere. Right? Additionally, since I'm using the kind of logging ability, it's very easy for me to turn that on or off, that I'm not constantly like making changes in my code. Cool. Now, this particular challenge, in fact, all of these, rely on you creating a primitive. And this primitive exists as a race, because we saw in main that this is a thread server. So every time we connect, it spins off a thread, and then that thread will respond to the commands that we have here. And there is a race condition. The race condition exists in the check on whether or not a given index has been malloced or freed. And let's find that guy here. This stored array. So this stored array is like a global state of whether or not a given index holds a malloced pointer that we can use, or a freed, or the address has been freed and we cannot use it. And so what we want to do is we want to rapidly flip this flag while simultaneously trying to access something that we can't. Right? Does that make sense from a race condition standpoint? Because we have this check here, right? For let's do printf. I am in printf. Perfect. And so if I don't free these, let's demonstrate the functionality. Well, I need a printf function now. Gosh dang it. Okay, well, we can do that. It's going to take a remote. It's going to take an index. And what is it going to do? It's going to say remote. I don't think I should use the word remote in context. I'll make it just R. R, send line. What is it? Printf, followed by index, and that also needs to be an F string. Now, one of the problems that you can run into, and this is an example again of why having these functions is good, is we're using these remote connections, right? And so that's connecting just over a socket. There is a limit to the size of these buffers. Right now, am I reading anything? No. So anything that the challenge spits back, which right now doesn't look like anything, right? That gets stored in this buffer. That buffer can get full. And if that gets full, like everything just kind of jams up and becomes a problem. So something that I may want to do in these functions is just every time I do this, let's clean. Let's flush the buffer. Because then I know every time that I've called malloc, I know the state of things as far as this buffer, as far as my program. I know everything is written out, and I've read everything back in. Again, this is just good practice. Now for printf, I probably don't want to clean because I want to obtain this value. So let's do a couple things here. Let's have an info that says printf value and then val, but I don't know what val is yet. And I need some val. So if we take a look on the right-hand side, if I what am I doing? Down here, printf r1. Instead, let's do r interactive. Let's run our exploit here, and it is mad that I stubbed out something because it turns out question mark, question mark, question mark is not Python. Okay. So I should be able to printf 1. And what I get is message colon something. And then if I were to, for instance, free 1 and then printf 1, we get message colon space none. So now we have some idea of what the behavior of this printf is. And we see that right here, where fprintf is called, it is in fact all caps message colon space and then the value. So this is good. So let's make val be our receive line. We'll drop the new line because I don't care about that. And then what do I not care about early on? Well, I don't care about this message stuff. So we'll do a receive until message colon space. Okay. That feels pretty good. And then my printf should return val. Because I may want to actually use this value, I don't just need to print it out. Right? And so now instead of interactive, let's just verify that this functionality works as we think. We have an empty value, right? And that makes sense. That's what we saw before. And if I free on remote one on the remote index 1, and we run this, now we see our value is none. So we are properly capturing that value from printf. Right? And then this is just kind of like basic writing skeleton functions here. Now I am getting some grief, which we see here. It's warning me about the bytes. So let's see if we can clean up any of that. If this is an F string, I think I want to encode it. Is that what I want? Does that doesn't blow up?
You can also just wrap it in, I think, bytes.
Just wrap it in bytes?
Yeah, or the bytes function.
I don't know which one is cleaner or shorter there. Here's my receive until. That one I can prefix with a B. We're making all of these go away. I want all of these warnings to go away so I can focus on the information that I'm printing out that's helping me reason about what's going on. Okay. What else is it complaining about? What line is that? I don't know. Don't care. All right. So I have this. So far, so good. Now we said there's a race, and in order to trigger a race, I need to have multiple connections. So I probably want more than just R. I probably want like R1, R2. Now, one of the things I don't know, you'll have to tell me, if the pre-recorded lecture videos talk about like warming up the T-cache. Do they?
I don't know if he specifically talks about it, but like the way he leaks a heap pointer basically warms up the T-cache.
Okay. So like right now, we have two connections and the T-cache is empty. Both threads have their own heap. There's nothing on there, right? And hopefully, from the previous module, we have some idea of kind of what the primitive we want to do. Ultimately, we want to overwrite the next pointer and then get the malloc call to return us a pointer to that value that we've written. Okay? So the first thing that we probably want to be able to do is print a next pointer. Right? We just break it down. Well, what is the next thing we want to do? So let's have leak next pointer. Now this one, because it's a race, is going to need two remotes because I'm going to be doing something on both of these. So I'm going to similarly have R1, R2, and then let's also have an index. So let's assume here I want a malloc R11. It's malloc R12. Let's free. Let's free. Cool. So what is my kind of strategy here? Should be similar to what we had with, I think, the pre-recorded lecture videos, where we want one thread to hammer malloc free, and we want another one to call printf, right? And the goal here is that inside of printf, the free function, the malloc function set stored, and the free function clear stored. So inside this printf, what we're trying to achieve is get this stored check to pass, but actually print the unstored, like when it the next pointer, which is after stored has been cleared.
Can we not just malloc after we freed and print out the next pointer that way?
Okay.
Because malloc doesn't zero it out.
So the question is, can I malloc free? So then in this case, you would look at my screen. You want to print F on 2?
Yes.
All right, let's see what we got.
Yeah.
What do I want?
Or malloc first, then print F on 2.
Okay. Oh wait. Oh yeah, we have the technology. What are you grumpy about? P process. Oh, we're grumpy because of this. Okay. So that did work. I did get an X pointer. Well, that was easy. Super easy. What if I want to set the next pointer?
Then we're going to have to do some racing.
Okay. Now, does it make sense right now to turn what we just did into a function? I don't have an opinion on this one.
I did, because I'm going to be calling it for every one of my outputs anyway, so might as well make it obvious this is boilerplate or whatever.
Okay.
After I did the function, don't think about it.
What do we call this? Get heap footer.
Sure.
And that only needs one. Right? Now, for our get heap footer, what is it doing? All of this?
Yeah.
Yeah? You want to do all of it? You want to fire it all off? Okay. The thing to keep in mind here, and the reason that I asked, is we need to track, at least mentally, the state of the T-cache.
That's true.
Right? So one of the things that somebody asked, how do you deal with a page fault? It could be a bit more specific for me, like seg fault in general. Don't access bad memory. Like that will happen, and we'll probably get there if I plug along at a decent clip. But like the thing that this does now is our get heap pointer. We need to keep in mind is the malloc free puts, and then malloc. We've done a couple things now, right? Because remember when I had just my basic ones like malloc and free, the state of kind of the world was known. It was constant. Everything's flushed. Everything is, it's a known thing. But now I have this function here, and it is expecting some things of this connection already, right? So like I can't, if I were to call get heap putter, and I've already corrupted a next pointer, I'm going to blow up, right? Because if I've overwritten it and it's bad, I could try and malloc something that's invalid. I get an alignment error. All of a sudden, things are nasty. And so what I try and do is make sure I'm very conscious about what functions leave the T cache in the world in a changed state. Right? It's totally fine that this is here. We just have to make sure that we have a mental note of that. We don't call this thing anywhere else because it is doing a couple things. And in my opinion, what I would do after this printf, as far as like that world thing, is I would free again.
Yeah, I was about to ask that, yeah.
Because now I am back to a set state where I started. I could still blow up if I overwrote this next pointer.
But you don't have this like random malloc hanging around,
Yeah.
throwing off some of your counts.
Exactly. Now, if I were, this again goes to why writing these functions is useful. If I were doing this in all just one continuous line, I would have to like attach GDB and then inspect the state, what's going on in store, what's that. But if I write kind of these atomic functions that either are mutating and changing the world or not, then it helps me have a mental model that makes me drop into GDB and look at things a lot less. So if we're going to have that, I would want get heap pointer to not be a changing thing. And so I'm going to have just a warm-up function. Right? Because this is clearly a mutating. I'm making this up as I go now, but mute warm up, right? Like clearly this is changing the state of the world. I'm going to warm up both. R1 and R2. And then we can get heap pointer. This is going to be a series of bytes. It will probably be 6 bytes, right? Get heap pointer. So then what I probably want to do is turn this into a number, which would be U64, and then I want to ljust it to length 8 with a null byte character. And then for our own sanity, let's cut this out. Heap putter. Heap putter. Heap putter is missing an argument. Yes, it does. Now, I'm going to ask this, and hopefully we get the right answer so we don't have to do it. If I were to run heap putter on R1, and then I run it again on R2, am I going to get different numbers? Am I going to get different numbers?
Yes, because they have different T caches.
Yes, because they have different T caches. And not only do they have different T caches, but they have different backing heaps. So one of the things that I know was mentioned on the Discord, I'll say blocking, hit enter to exit. Let's do that, and then let's do GDB attach on P. And for silly reasons, you must deroot U64 L-just. None type has no attribute. What have I done? Get the pointer. It probably helps if I actually return something. I'll just 2 arguments. Argument 2 must be, yes, I didn't make it a byte. It is currently cool. And so now we have this heap pointer, and we have GDB attached here. We can sanity check ourselves as far as what is coming out of here with does vmap on pwn.debug not work like that? That makes me sad. Copy that. Okay, apparently not. Does anyone know by chance the pwn.debug command to quickly find out what region?
Is it not VMAP?
You saw me just do it, right?
Yeah.
On Jeff it does.
This is actually part of it. Do you demangle something?
Oh, that's right. Safe linking. Safe linking is here. Okay. So we leaked what was in the next pointer, right? Or we printed it, but we haven't demangled it. Good call, sir. So what do I want to do next? Math. All right. Okay. Did anyone actually read? I thought I was going to get more likes on the old write-up I did. That actually took me a little bit of time to write all that out, guys. But yeah, that's okay. Did we just steal the magic function? So there's 2 magic functions. You will need both. There's mangle, which takes a position in a pointer, and it returns
Position, shifted by 12, Zord with pointer.
Okay. And then this is, you can always use mangle. Like everything is really a permutation of mangle. So like the one-off demangle thing, everything else all built upon this core mangle function. So depending upon what kind of madness you're doing with position and pointer, it may make more sense to just figure out what values should go in mangle.
Yep.
Which you probably experience in the later challenges here. Okay, what's our other magic function here? We have a magic demangle that sometimes works. And if you want to know why it works and why it doesn't, I think that's a fine thing to look at last week's office hours or the write-up that I posted on the Discord. But this magic thing is what?
It's like a bid value. That's the mangled pointer Zord that's self-shifted by 12, I think.
Mm-hmm. Now, some people ask me, and it's fair, like this is an optimized version, or it should be mid by 24.
Yes.
I do actually know what it is. Sometimes. If I have enough caffeine in me. So, this is like, where does this 24 come from, right? And I don't know that that was effectively communicated. Essentially what we're doing here is uh, 12, 24. This. These are the same as far as what they do. It's just that one note that half of this and the other half of this are the same thing, just bit shifted by 24, right? A bit shift of 0 shifted by 24 is 24. A bit shift of 12 shifted by 24 is a bit shift of 36. Right? That is where this mid value comes from. Right? But if this seems like just kind of magic, magic crypto XOR stuff, we write it out this way and it'll do the same thing. Cool. So I have my demangle function. What is the implicit assumption of this demangle? What must be true for this demangle thing to work?
Should be the same page, at the same page, the position and the pointer.
Yes, the position and the pointer must be on the same page, those two values. Now, if I am starting a brand new thing, right, a brand new heap, and all I've done is malloc, free, and how big are these allocations? If I remember right, hex 400? Is that right? Let's find it. Am I just blind? Yes. Okay. Hex 400. So doing 2 mallocs will still be on the same page. So assuming that we're starting at the beginning of a page, right? We could be at the end, and then that would not be true. But assuming that it's fresh and we start at the beginning of a page, malloc hex 400, malloc hex 400, free 1, free 2, we will be on the same page, which means that assumption should be true. So our leak next pointer then, where am I? Heap pointer, meet warm up, get heap pointer. Get heap pointer. It probably shouldn't return val, it should return demangle val, right? So we probably have a problem here. What's our problem? I could run it and get the error, but this time I saw it before it yelled at me. Our problem is the type, right? Demangle is going to do these XOR operations. That needs to be on a number. Printf is going to return me bytes, but these bytes are going to be the characters, the bytes of the characters of the number, right? No, I'm wrong. It's just going to be bytes. But I still need to turn it into a number. Yes. There was a problem. It just wasn't that problem. All right. So let's do that. Now this becomes val ljust, and this will be heap adder, and we will demangle heap adder. And then let's print that guy off. Let's get heap footer on. Just a connection. All right. So far, so good. Does that look like something? No. Putter is not defined where. Putter, that's because I called it mangled putter. And let's do the GDB attach. Okay, I've got a pointer. and it exists. It's in a read-write region. It is in one of these anonymous pages that was created for the thread. So this is going to be where the thread heap is. All right, this looks good. Right, we have something that we know. So far, so good. All right, our next task is we probably want to be able to overwrite this next pointer. That's where the race is, huh? Is that where the race is?
Yes, because we can't overwrite. Well, we overwrite it while it's malloc and it's free, but we can overwrite it again. So to overwrite when it's free, we can't overwrite when it's free because the stored flag is blocking this.
It's R1 interactive. Does all that. And so right now, this is, that says, I think my free function, it does say free. Oh, I'm not logging it, that's why. Okay. Yeah. All right, so now we have this nice pretty output so we can track kind of what's going on. I have my heap pointer and our write command is scanf. Right now, 2 is freed and 1 is also freed. So if I try and scanf into 1, hello, and then we print F1, I get nothing. So that didn't work. If I malloc 1, and then scanf to 1, hello, we can get hello, but then when we free 1, it is none, malloc 1, print F1, and now it's overwritten with that next pointer. Okay? So I can't overwrite the next pointer itself directly like this without going into that race. So let's make something that races. I don't need a fancy leak next pointer because we did that with get heap pointer, and that guy was kind of a one shot. So now, what do I want? I want set next pointer. Right? And you'll note that I'm giving this an index here. And that's because there ultimately has to be one index that's like the hot index that we're fiddling with. And I'm going to specify that in my set next pointer function. Because as time goes on, we'll find that there are 2 things that can break as we repeatedly use these primitives. We can break the T-cache, right? Because we've written some invalid value and then we try and malloc and then it explodes. And the other thing that we can break is we can break the indexes themselves, where we can get that in some unusable state where 1 is now a bad number, right? We don't want to do anything with index 1, and for that reason, it can be useful here to have a index value in your set. Somebody says we got a couple here on Twitch. What's the purpose of mute warm up? So mute warm up is just putting a couple things in the T-cache. Right? Mute warm up is just malloc, free, and so that gives me 2 entries in the T-cache. Now, in my opinion, what I would do, like long term, is I would probably malloc more than 2, because I may need to like load these up ahead of time, right? Because once I start doing weird things with racing and overwriting next pointers, I become more constrained as far as what I can or can't do. This circles back to what I hope to close out on, which is like juggling pointers around the T-cache. Right? Like I said that you can explode the T-cache, right? You get it in an invalid state, you perform something, and then it says, hey, you're unaligned, or this is invalid, or you don't have the T-cache count value isn't large enough, then all of a sudden, like, things are not going your way. There's 2 ways you can deal with that. There's the easy way, which is just say, okay, screw it, right? Let's just close this connection Let's make a new connection. It'll have a new T-cache, but it'll also have a new heap. Right? And if it's a new heap, then that is now a new position value. And so that you have to factor that into all of your calculations when you are dealing with safe linking, because now you have two different pages that are being used, right? Which is totally doable, and you can do that, but that is more complexity you have to deal with on the math side, right? I'm less likely to, I don't care if I blow up the T-cache, right, or get it into a broken state, but I have to account for that in my math. Alternatively, what you can do is you can be very purposeful. It's not really the word I want, but very specific in the actions that you do with the T-cache, such that you always have one T-cache that is in a good and workable state. So, like my claim here, which I know is true because I wrote it, is that you can solve all of these challenges with only two connections. You do not need to throw away connections. And so this T-cache warmup is function, to circle back to Twitch. I don't know, I'm blinking yellow on my camera now and I don't know what it means. I don't know what shape I need to make. Okay. But you can solve all of these with only two connections, if you are pay close attention to what entries are broken and where you put them as far as these two T-caches that you have. Like the high level strategy is I have one good T-cache that I draw from, that I already have, for instance, this heap leak from, and then the other thread, what I do is you remember that game where you have the towers? You have the three poles and the rings? Towers of Hanoi, yeah. All right, you kind of play that game where you have this bad allocation, right? And you throw it off and you push it onto the T-cache that you don't want, right? And so you have one good T-cache and then you like pop one off into an index and then you push the other one onto the garbage T-cache to keep one T-cache in like a golden state that you can use. Right? Like that's how I think of it. Twitch doesn't believe me, and that's fine. We'll see if I can actually replicate this on the fly, but it can be done. All right, so I have this. What do I want? Set next pointer. That's where we are. Cool. This is where we got erase. So our strategy is thread 1 will malloc free. Thread 2 is going to call scanf. Now this is one way that you could do it, and this is probably the most optimal way you could do it, but it's going to have some problems that I don't like. So we want fork from OS, import fork, and then from sys import exit. And then I also want wait from OS. Could you use Python threads? Maybe. As you hopefully know at this point, Python threads aren't real threads, so you don't get true concurrency. Or maybe you get concurrency, but not parallelization. I don't know. The words mean the same thing. You're going to have better odds calling fork. So I want to have some PID that is going to be fork. And then if PID, or let's say if not PID. If not PID, then this is the child. The one thing I want to make sure I do is the child exits. Otherwise, this blows up into a giant mess. So my child I'll have be this thread 1. So I'm going to have some command string, right? And that is going to be something to the effect of malloc index free index based upon my current strategy. One thing that's important to note here is I do have a space at the end here. Why is that important? Because the very next line that I'm going to write is command string equals command string times 40. Can you write this command string repeatedly in a loop? Yes, but we're trying to race, and this means we care somewhat about performance. It is much better to give it a long string with many commands in one write than it is to repeatedly go over the network and try and pass all of these. And so this is a performance optimization here. The space is necessary because otherwise this doesn't parse right. So then I want, sure, R1. Why am I blanking? Okay. Send line command string. And let's do this in a loop for, I don't care, in range 100's a number. All right. This right here is the parent. What do I want the parent to be doing during this time? Well, if I go back up here, I want to be calling scanf. So in the parent, which would be R2 for this example here, we will, do I have a scanf function? No. That's okay. We'll send line, and we're going to do something similar here where there is a command string, and in this case, it is going to be scanf. I probably want my function to have the value to write. That may be something I need. Now, this is one of the places where you can get trapped. If I were to do scanf val, and val is a byte string, what's going to happen? This is a common gotcha I've seen people do. So if I say A equals the byte string XOFF or XFF ABC, and then I print F A is A. It's going to give me the Python representation of the byte string, not the literal bytes. This is a source of great pain if you don't know this. I have done it many times. That's why I'm telling you now. So we don't want to do this. Instead, we want to append the bytes. So this is my command, and then I'm also going to include a space at the end of this for that same reason, because I'm going to have this repeatedly run the command. And as long as I'm talking about not writing horribly inefficient code, let's construct the string and then reuse it instead of reconstructing it 100 times. Now I need the parent to wait until the child is done. No need. Okay. So we can do that with wait. And that's going to, hopefully, as long as there's not any other crazy signals going on, when the child exits, a sig child will happen, which the parent receives. And so this should cause the parent to wait for the child to finish. How do I know if I succeeded or not? Because this is a race condition, right? So I could fail. What do I probably want to do here?
Mount index and then printf to see if you successfully wrote those bytes.
You say I want to. I have to think now. Malloc free, malloc free, malloc free, malloc free, malloc free. In theory, we freed, I wrote, we malloced. Okay. Just a second. I'm blanking. Okay. I'm just going to stumble forward, and hopefully this brain cloud removes itself. Okay. So the claim was that I want to malloc let's see, we'll do this on index, and we will do this on R1. It's worth paying attention to how I talked about like standardizing this function and having these things in a known state. I don't know this is what I want to do, but it's something to pay attention to. Where did this index come from initially, right? In here, we are malloc and freeing it from R1, so I want to keep it on R1. This goes back to the T caches are separate, the heap addresses are separate, the pages are separate. As soon as we start pushing allocations from one heap into the T cache of another thread, things become way more complicated. So let's keep all allocations that we care about as like coming from a single page here. So then I malloc this, and then I want to printf this, and that should give me a value. Is that what I want?
Wait, do you want to malloc 1 or do you want to malloc index?
You are correct. And then printf would be R1 on index, if I remember right. Am I consistent with my API? I am. Okay. So now I have this amazing set next pointer. That's going to take R1, R2, and we will give it index 1. It helps if you don't go interactive before everything.
Does you want to give it a value as well? Actually set it to?
I probably do want to give it a value, since that does require 4 arguments. It's expecting a byte string, and I gave it a string. Well, that didn't work. Damn. So we are mallocing and freeing on. The lame thing is I just wrote this like an hour and a half ago.
Oh, your scanf call isn't correct. Thanks, Chip.
I don't think this is. We're still not getting what we want. I think we're thinking about this wrong. So we are mallocing and freeing on index 1, and then we are trying to rapidly overwrite this between malloc and free. Because we were trying. Set next pointer. Malloc free. Let's make. This is right.
We're just not trying it enough times.
No. So like we can check that and we can loop it, right? I'm trying to think about there's a problem that I know exists here that I'm trying not to deal with in the immediate. if we are malloc and freeing, then we should have it be malloc, and then we want to get it on the edge case of it actually being free while we are calling scanf with the value. And what should happen is this should, when we call malloc, yes, we call malloc, we check this, that should be the next point. Okay.
Are we actually doing anything with the printf call?
Our printf prints it out in the log, but like we aren't doing anything with the value, right? But in this for loop, we would need to say that the found next pointer would be this. Is this formatting it? No, it's returning this bytes. If found pointer equals hello, then we break out of this for loop. And let's print success. And then let's always print found pointer. Something. This class ends roughly 45 minutes from now. Yep. Somebody says, I'm racing between free and printf. You're doing scanf1. You're racing between free and printf, not scanf. What are you saying, Twitch? You know, I say quizzical things, I admit.
It's like we're not predicting the loop either.
Right, so like this isn't, so something is,
Are we like calling it incorrectly?
what am I doing wrong here? This is now Robert can't write Python. Malloc index free, that's good. For blank int range, we send line command string, that's fine. That exits, that definitely, oh. We probably want to fork every time that we're doing that. Okay.
Oh, we're getting the A's.
Now we are getting the A's. That's because I checked for hello instead of A's. I should check for value.
But it looks like we won the race.
Correct. So we were able to do that now. So we were able to set that and get that returned. Yes?
Cool.
Hooray. Twitch is just full of traps, man. I need to just not ignore Twitch. Because like I look at it and then I think something and I'm like, wait, what are you? Then the cloud of uncertainty just gets deeper. Okay, log info success. I don't need to print all that. So we like this so far. We can set a next pointer. Yeah, I got a thumbs up.
Can we follow a next pointer?
Can I what?
Can we follow a next pointer?
Can we follow a next pointer?
Is it like actually allocated?
So yeah, the next thing that I may want to do is what do I want to actually write? I probably don't want to write A's, right?
I want to write a pointer that we can access to do arbitrary reads and or writes.
Yes. So now I need a point of interest, right? What am I interested in? Let's look at challenge one. What should I be interested in? Does this thing,
It's got a secret.
does it have a secret? The secret is stored in the BSS. Okay, that's great. Does this thing... Sweet, no PIE. So this should be straightforward. And let's see if we can just do this right off the cuff with the power of Python and Pro Tools. So we'll say E equals p.elf. Then I want the value that I want to write. This is again, design choice on your half. Do you want to write the literal bytes, or do you want this next pointer thing to deal with safe linking itself? Because if I just write the raw address, it's going to fail. Right? When I try and malloc it. It wants I need to write a mangled value.
I'm trying to think if there's a case where you don't want to mangle the value.
So in our use case, there isn't.
Right. Like theoretically, there may be some point where you like.
Yeah, where I already have something that's mangled, or I need to do some greater manipulation, we'll say.
Right.
Where it's not just a simple question, off topic, of course, Twitch. Why would you ask something that is topical? But is the ELF base at hex 3EF1000 instead of hex 4000 because of the libc linked? That is an interesting thing. I actually don't know why that is there. I wouldn't blame libc unless you can prove that that is the case from patch elf itself, because the way that these elves use the other libc is from patch elf. So if you were to build something that's no PIE, check the base, patch elf, and then see that the base changed, then I would say yes. Otherwise, it would just be an unknown for the ages. Okay, so I have my mangled goal is going to be a mangle of, what's my mangle function? Position and pointer. The position is my heap pointer. I can use this heap pointer because the heap pointer should be on the same page, and then technically we could say this is, I don't know how to do what I want to do, but the least three significant bits don't matter, right? Because it's bit shifted by 12, so we can just use it here. We could zero them out, but I don't want to break this because I can't do basic logical operations on the spot. And then my goal is E symbols. Does this thing have a name?
I don't think so.
It doesn't have a name?
It's sort of like being a thing, I think.
Secret correct. Load secret. Load secret sounds great.
Load secret takes an address to put the secret into.
Load secret takes the address? That's sad. Okay. So we have to find that guy then, don't we?
I think if you just look at, I think it's in like the decal code. You just go to main where I think it's set.
Where am I? Secret correct. You want to go. Let's find main. My searches, yes. I can hit a key. All right, and where do you want me to go?
Scroll down a bit. You should call. Yeah, there we go. Load secret with that thing. Just add
Okay.
that.
You just want to grab that. 405 4C0.
5460.
Fine, we won't use the fancy. Even if it didn't have symbols, what I would have done is I would have gotten the BSS address and then just added an offset from there. But if it's just this hard-coded thing, that sounds great as well. 4054C0. Ooh. One quick way to find the secret through pwn debug. All right, this could be a good nugget.
Oh.
Let's see. Let's see if I can replicate whatever is
The
happening.
practice secrets are all the same.
The what?
The practice secrets are all the same.
Oh.
Because it's just generated from the seed of the flag. And the flag
Oh no, that's true. That's true. I never considered that. More cleverness. GDB challenge, baby prime level, whatever it is. No, GDB challenge, baby prime. I just want to do this on stream. Type the random commands that the magic internet man says. YQMSXTHD. Okay.
Ooh.
Okay. That's pretty slick.
Nice.
Somebody else says they use that a lot. Yeah. Well, hopefully. Now, is that? Okay, so specifically search, and that's got to be a pwn debug. You could probably use, yeah, you could just use GDB's built-in find too. You'd have to specify the range because the base command to find has a start address and an end address and then a pattern. And so you could do that too. I don't know how I would do that. Cool. Okay, that was an aside. So we have this, we have our mangled goal. Hopefully we are mangling things correctly. We'll delete to this. We write our mangled goal. Now what do I probably want to do up here in set next pointer? Based upon like good housekeeping habits that I've reiterated here. What's that? I could, yeah, so I could pack the address up here in set next pointer. I'm going to say I should do it here. And instead, there's something else that I should do. That was a good call.
Twitch chat says you should free stuff.
Yes, I should free stuff. Thank you, Twitch chat. Oh, wait. You said something useful?
Monkey's typing sometimes will do good things.
So the reason that I'm freeing this is because this malloc here at the end that I had to do to verify has changed the state of the world, right? And so I want to make the world be as close to what it was when I started as when I leave. And so the only thing that has changed here from calling set next pointer is we've set the next pointer, right? And that's ideal because now our function does what it says on the can. Versus if we didn't free this, all of a sudden our T-cache and our indexes are not in the same state that we left them in. And this is, again, is why having kind of these atomic functions, these primitives, is useful. All right, so we have our set next pointer. The next thing that I want to do is we'll malloc R11 and we'll malloc R12. And in theory, the setting of the next pointer, the malloc should give me a pointer to the secret. Yes? At which point I can print F R12, and this should give me secret. Let's see, are we believers?
Moderately.
What's that?
Moderately so.
Moderately so? I'll take that, man. Moderately so is pretty good. I think statistically at this point it makes way more sense to be a doubter. Because of things like this. Mangle heat pointer poor. Where did that come from? Up in my mangle function, I typoed. It's not poor its position.
We're really trying to race here.
Things are not going well. But we see that we're like consistently getting the same value.
Yeah.
Well, what could be wrong? There is something wrong. Like I would argue that we probably did the overwrite. I bet we won the race, but there's something wrong with our logic here on escaping this loop.
Oh, are we only breaking out of the inner loop? Or no?
Well, we are doing right here. If the found pointer equals val, right? I'm going to print, we'll see if I'm right here. The length of found pointer length found equals this. And then we'll print the length of val. Like this. See our problem?
Yeah.
So when we have a val, we said that we wanted to pack this to 64 bytes. And so we're expecting 8 bytes to get returned by printf. But printf is not going to do that. Why? Because these last bytes are null, and so it'll stop printing them. So instead, we want to do something. I'm just curious now. If I just had like thought, it's scary. If I do like hex 01, hex 02, I want to know if I can strip a byte string.
Oh.
Like that was the, okay.
Nope.
But can't you, I want to say you can do that. Yes. Like we could do some type of length check and then reduce it, but there's going to be, it's less generic because we don't know, right? Like if I were to hard code, what did we have here? 5, right? 5 will not always be the length that we want. And so if I were to hard code this value, it would cause problems in my primitive when I reuse it and suddenly the thing that I want to write is 6. But what I can probably say is that I don't want any null bytes here. So if found pointer stripped it of null bytes equals, and we'll say val strip it of null bytes, then we declare success. What do we do now? We got success. We mallocked. We got a SIG abort. What probably happened? What's the common case for SIG abort?
Either we didn't go to someplace that was 16 alive, or we mangled incorrectly, quote unquote incorrectly.
Okay, so we're probably blowing up on this malloc right here. And the question is how or why, right? Because it could be because we are unaligned. It could be because of.
We're blowing up the first malloc or the second malloc?
So what I did was we're probably blowing up in the second malloc, right? That is what I would expect, right? Because that is where the value that we wrote becomes an issue. And so what I did here is I just commented out the spot where I expected blowing up. I'm attaching GDB instead and saying, all right, cool, let's rock and roll. Why? Because now I can use GDB and say thread 2, and then for pwn debug, the magic command is tcache bins. And what do we see happened here?
We're off by 1.
We're off by 1. That is a bummer. And what is secret? I don't care. Give me. Now, is this? My question is, which is the problem? Is the problem that we're mangling wrong, or is the problem the address itself?
We're mangling with the wrong position, probably.
Okay, the claim is we're probably mangling with the wrong position. Possibly. Can we know which it is?
I don't know how we know for quickly, but I solved this problem by adding a bunch of stuff or subtracting a bunch of stuff until it turned out right.
Right. So you could, and this is where. Why are you doing that? Can you just give me? What do I want? Okay, I want that. Let's do what's interactive. Who's interactive over here? Let's free 1. Let's tcache bins. What thread am I on? Thread 2, tcache bins. Okay, and this is what I got for the first allocation. What is my leak over here? Did I print it out pretty?
There is.
Okay. 7F976C 001. Huh. So what happened here?
Did we no. I think we did demangle that pointer, right?
Mm-hmm. No, we demangled it. So we implicitly assumed way back at the beginning that if I malloc hex 400 and I malloc hex 400, that I'm going to get something that is on the same page. That was our assumption. Do we know that that's what happened here? Because if we were to look at the region of memory that is this, where is the beginning of this? We didn't get a pointer to the beginning of the page.
It's in the middle of the page somewhere. So.
It's not the middle of the page, it's the second page, right? Yeah, the first allocation, well, wasn't where we thought it was, right? And so there's a couple ways we can deal with it. Instead of doing malloc, free, we could malloc free and look at the value that's there. That's always a useful value to have. Hint, hint, nudge, nudge. other thing that we could do is we could just say, all right, this is the next page and not the page that I'm interested in, right? At which point, what I really need to do, and I've done this a couple different ways historically. I'm not happy with any of them. Is the location that I want is heap pointer -1, right?
Or, wait, you want -1 or -1,000? Or extra 1,000?
Yeah, this isn't shifted, so you are correct. Because like you could put it up here and say I want to go down a page. Another way that you've done it, which I kind of like, is in your demangle function. You then have an offset, and you use this offset value in your math down here. There's a few ways that you can address that. I think this is the cleanest or most straightforward way. Having fought this problem many times. So let's drop off GDB. Okay, we got a printf value that is the secret there. So we were able to leak this value. Success. And I would argue that the key to doing so was making sure that our functions up here were very clear, very distinct. They weren't having side effects, et cetera, et cetera. Do I need to take this all the way to the flag from this point?
No.
Good. This isn't a full solve. Okay. So that was useful and hopefully is the primitive that you need to then start working up for later challenges. Because the difference here now between level 1 and level 2. Level 1, okay, we're hiding in the BSS. Level 2, all right, we're hiding in the thread heap. And so now the problem becomes, right now what we did is we created the ability to arbitrarily read. And so what's different now is where am I reading? And this is where the further reading link, right here, is extremely helpful. This, along with the pwn.debug P2P command, will allow us to kind of say, well, what is the chain of things that I need to read to get to where I want? Right? This is what I was rambling about on the day of class and then showed nothing of substance. It was a great ramble. I just need more time than like the 40 minutes that I have. So if we have good old pwn.debug on here, we have VM map, we can P2P, and the one thing that I know right now is the heap leak, which we have right here. Where's that sweet number? Heap pointer. So my heap pointer is on this page. So I could find or calculate the location of anything that is contiguous with this region of memory. And that is A6C. It's a good thing to realize that A6C, there is more than just this page that I can access, right? We look at the end is equal to the beginning. The end is not equal to the beginning, so I can't go any lower there. I've got these two pages. Is the end equal to the beginning? No. So I could search anything that has this here. And so we can P2P this. And what am I interested in? I don't know. Let's see. Right? There's so many. Did I go backwards? No, I did that right. I did that right. And so if I wanted to get a libc pointer, we could do the exact same thing that I did, except instead of my target being 405 4C0. My target is the difference between, we'll take this one, this guy minus I should have just saved that value. We've gone too deep. I have it right here. I'm going to guess that libc is higher, or that location is higher. So this is my heat pointer leak. And so we print that, we get some constant value. And so instead of leaking the mangled version of this, if I wanted to leak, for instance, that libc pointer, my mangled goal becomes mangle heat pointer minus hex 1000, because the location that I'm doing this is still the same, but the value that I want to write is heat pointer plus like that, right? And so this heat pointer that I leaked is serving two purposes. It is serving as a proxy for position, and it is also serving as a location into a region of memory that I can calculate a distance to something else that I'm interested in. Is that a jive for everyone here? Cool. Like this is the two key things here is writing code that's clean, and then understanding that you can calculate the distance from any pointer to any other pointer as long as the region of memory is contiguous. And so we use this to then get a libc leak, right? Then I could search libc for, I don't know, what is baby? There's some pointers into the binaries region of memory. And so we just do this repeatedly until we dance around all of these different regions and we find a chain of leaks that we would read. Then we get this new value, we calculate a distance, we read, we calculate a distance, we read, okay, there's our secret value. That is the entire strategy here. And that's why the pain factor varies depending upon how well you progress. All right. Any questions about what we've done so far? Yes.
Does the mallet function check whether the address is end up with 0 or other number?
Okay. So the question was, does the malloc function check if the least significant nibble is 0? And so we can do that right here. I could change this to a 1, right? And that should either work or not work, and that would answer your question. Is that correct?
Yes.
Okay. Let's do that. And I'm going to comment out the second malloc, because this is the malloc that would trigger that. And we'll have GDB attached. All right, that runs. Here is our GDB session, which we can continue. And if I run malloc 2, we see that we do blow up. And we are getting killed. Do we get to see the message? We get killed by the SIG abort. And it doesn't show it. Okay, let me see if I can get that. The answer is yes, right? It is checking for the alignment. That is in all of the challenges in all modern Linux has that requirement for the Tcache. Where anything that's safe linking, they detect corruption. That's one of the corruption checks. Is that this address must, when demangled, end in 0. I want to see if I can get that message though. Let's do print p receive all decode. And let's decode it left. And I wouldn't need this. That. Let's see if we get the message here. It helps if you close your strings. Cool. And so we see the message right here. Now, why didn't I see that originally? Because the message, like the actual crash, isn't happening over the network connection, right? Because R1 and R2 are the remote network connections into this process. But that error message is getting printed out over standard out of the main thread. And so in order to capture that error message, I needed to print everything that was displayed by the main process, by the main thread. And so now we see that the Tcache is complaining about that being unaligned. So yes.
So if there's such a check, so how can I deal with the next 8 bytes of my secret? Because I need to write something like 405 C8, right, to get a.
You're saying, what if this is what I need to do?
Yes. So how can I deal with it? I cannot manage something.
So there's a number of, I don't know specifically like what challenge has this. It wouldn't surprise me if this is a subproblem in there. But if I wanted to do this, there's two things, and it would depend on the scenario, right? If I want, do I want to set this value or read this value? What do I want to do?
Read.
I want to read it. Okay. Well, if I did C0, I'm going to have a bad time, right? Because it's going to, when it is malloc, it's going to clear the address plus 8, correct? But what I could do is I could go to B0. Yeah. Right? Like B0 is a good place. I want to get C8. But if I can write to B0, then I could do this. And then what I would do, this is where, Robert, you don't have a scanf function, suddenly matters. There's my printf, def, scanf, r index, val, r sendline. In this case, I want scanf, then I want index, then I want val. And then we will clean as well. Yes. So I'm going to go for B0. And so this right here should return my B0 pointer, correct? And my goal was to scanf null terminates, doesn't it? Doesn't scanf null terminate?
I think so.
Dang, then what I was going to say wasn't going to work. I was going to say that we could go to B0 and then we could write, that would be 24 bytes up to it. So then when printf calls, it goes through it. I think scanf does null terminate. String input, store the terminating null byte, yes. Okay, so I couldn't do that then. But if this used read instead of scanf, I could do this and then read up until that, if I read in 24 bytes. Then when printf called, it would A, and then the value. Right? And so one thing I could do is I could go behind it. If I'm trying to read it, that's probably the most direct way to do it. Now, if I have to have scanf, then I need to be more clever because I can't use this directly, as you point out. And so I'd have to be like, okay, well, what else prints things? Is there other functionality here that prints anything? Well, the answer is yeah. It's one of the key insights of one of the later challenges, and so I don't necessarily want to spoil it. But instead of directly targeting this address, maybe I want to target an address that is used by the program elsewhere. What do I mean? This is tough to demonstrate without just giving it away in the challenge. So let's say I have some program that does char star magic string pointer, and then there is some function print stuff, and it is going to call printf %s on magic string pointer. All right, so let's assume that I have an arbitrary right somewhere up here. Right? I have this primitive here. What would happen if I overwrote magic string pointer and then print stuff was called? All right, so magic string pointer is going to equal char star some const hello world. Right, during normal operation, this thing just prints out hello world, right? But there's a layer of indirection here in how this program works, because it's not really printing out some const, right? What it's printing is magic string pointer. And so if I could use my arbitrary right to set magic string pointer equal to, what did we want to have? OXC something, I don't know, B1, right? If I were to do this, right, what was our magic? 405 4B. 405 4 B1. What would happen if I managed to do this? What would it print?
Something inside the 405
Right. Is 405 4B1 aligned? No. Is it a problem? No, printf doesn't care. Right? The function that cares is malloc. So this is what I mean when I say there's a layer of indirection. Right? If we have an arbitrary read, but I can't get exactly what I want, can I change some other part of the program's functionality to get it to do what I want? Right? And I believe this is a problem in one of the later challenges. Right? So safe linking, as it was kind of described at the end of the prior module, does stop a subclass or subset of heap exploits, right? I have to make, if I get an allocation, it has to end in 0. That's just a fact, right? I cannot get malloc to give me anything that doesn't end in 0. And that is part of the design of those last like 4 or 5 challenges of the previous module. Is some things are a huge pain because safe linking just says, no, you can't do it, right? Other things, depending on the scenario, maybe it doesn't matter at all, right? And that's why a lot of people were like, hey, 16 is insanely hard. I'm going to like try these other ones. Because if I remember right, the very last one like requires almost no change at all. Right? And that was like by design. I didn't put them in order of ease. I put the harder things first, and then when you get to the end, you're like, wait a minute, it didn't make a difference here. And that's right. The mitigation or the amount of pain that safe linking causes the hacker depends on the scenario and what you're trying to do and what bytes are involved. Which brings up one more thing. Twitch is just going to have to trust me that you can do this with 2 connections. Because I don't want to go keep these guys any later than the 2 hours that is already exceptionally long, but they seem to enjoy it, so I target 2 hours. One thing that I didn't run into in this exploit, but absolutely will become a problem, which I mentioned, was evil bytes or bad bytes from ASLR, right? So what I would suggest you do is when we have like next pointer, there's this value, okay? I would, right up at the beginning of this function, instead of running this 100 times, it blows up, we'll just say if, what's a byte that we don't want? Well, we don't want, well, no bytes are probably okay. Tab. If tab is inval, we will just raise an exception. Right, and I think you can do like bad byte.
Yeah,
You can give it a message here. Then let's bring all this over here. So we have def do thing, and we can say try while true, try do thing, and then we accept. We could either pass or continue. For those that don't know, pass is just like this Python keyword that is essentially just a no-op, right? It's do nothing. Either one of these would allow that loop to continue, right? And maybe we want to, for our own sake, print, exception occurred or something. And you could use this logic to whatever degree you want. In my opinion, it's a lot better to fail fast, fail early, and fail obviously. You want your exploit, if something is wrong, you want it to die and just scream as loud as it can, this is the problem. You do not want it to silently say, okay, well, we're going to like pass this other value that's going to go to this other function that then you're going to compute something on, that then is going to do some math, that then blows up 4 functions away, right? You want it to fail fast, fail loudly, and fail obviously. Now, tab isn't the only evil byte here, right? And that problem exists not only when I am trying to set the next pointer. Right? This will be an exercise for you. There are more evil bytes. What else could happen with evil bytes? Where else could this be a pain? It's not only when I'm setting like the next pointer here.
Like, well, when you're reading it in, like, I just stop in the middle of a pointer because there's a null byte in there or something.
Wait, there could be a tab character inside something that printf returns, right? Or it could be a null byte inside of printf. And so that means inside. And maybe I don't want to do that. Maybe I want that up here. Is there an assumption? Like maybe I give this assumed size, which right now will be 0. and we'll do it right here. If assumed size does not equal 0, and the length of val does not equal assumed size, then we will raise an exception. And this will be printf bad length. Put these into these little sub-functions. Now, this printf that you're like, Robert, this was dumb. Why did you do this? Right? Well, now every time that I call printf, it will loudly fail if it doesn't do exactly what I think it does. If I started writing this as one giant function, every time that I said r send line printf1, I have to check the length every time in there. And all of a sudden this logic just becomes crazy. So these silly little wrapper functions allow me to assert things to be true. And in fact, instead of raising an exception, which is fine, you could also do this, which is just a programming thing. Assertions are cool and fun. Right? And an assertion is just, this must be true at runtime. If this is not true, raise an assertion, raise an exception. And we can do that same thing down here now. Instead of having this if raise exception, we can say assert that the tab character is not in val. Like this may have some type error with like something being a list or a container if I were to actually run this, right? And you'd have to clean that up a little bit. Yes. Well, that's just Robert can't type. That's not anything crazy. We passed all these assertions, so nothing blew up, right? But, oh, that is really not happy. If I were to verify my logic now, I don't want to infinitely loop this. And now inside do thing, what happens if I try and do the thing that is bad? We say mangled goal equals a tab character. Right? Why not kill? We run this. Now it's mad over that. Exception occurred. Right? And so we don't have to just say exception occurred. Again, you can use whatever logic you want. But now I know that I did something that wasn't allowed. Right? And you could, again, improve this logic to specifically assert this with an assertion message of tab character, invalid character passed to scanf, or invalid character found in printf, invalid length, right? And so that allows you to gain insight into what went wrong, why it went wrong, instead of just, I have all of these things and it just explodes constantly. Because you will do everything right and still explode sometimes. And so you have to be able to distinguish which, is the cause. Any last minute questions? Anything from Twitch? Almost 2 hours felt like 20 minutes. Yes, I know. It's way more fun here where I don't have like a hard cap on the time. I feel like we have a lot better sessions, but I'm glad that it went by quick. Love they joined an hour and 50 minutes late and they haven't missed that much. What? And then somebody else comes here for comedic relief. Slightly off topic. Somebody says, if you want to be extra efficient, you should start with index 0, not index 1, so you have more options for arb read, arb write. That's fair.
It's like when you screw up a pointer, you just keep going.
Yeah. So like one of the things that I mentioned is that you can screw up a pointer and then that index is just burned and you don't want to use it. And so starting at 1 to 15 is 15, but if 0 to 15 gives you 16 options, right? Hopefully you aren't burning that many pointers. But hey, if you are, right? Flag is flag. Flag is flag. I think we went somewhere, okay? It's not about the destination, it's about the journey. All right. I think this was a nice progressive journey. And yeah, we're past time. So let's call it. I appreciate everyone hanging out. Hopefully this was somewhat useful for you. I am going to release the next module some point this evening. If I remember right, that is Heap 2, which is a lot of fun. With that, I will leave you guys. Goodbye and good luck.